Okay, so we can now start looking from more distance on how a robotic system work. We have detailed at least kinematics and invert kinematics. We will leave to the differential analysis the next lecture. But now we want to verify how, see how robots are programmed. And on top of that, what is the general structure of a control architecture or supervision architecture, how do you prefer to call it, that considers tasks, considers components, sensors, actuators, and their interaction, and reasoning about sensing information in order to perform the tasks in the best way, when the task is not just as trivial as go from A to B and that's it. Okay, so our next slide will be divided in two blocks, one on robot programming. I will stay at the very generic level. We will not program robots. You have some course devoted to that, at least within the Master in Artificial Intelligence and Robotics. And the second part, which we'll most likely see on Monday, will be devoted to supervision and control architecture. Okay, having said this, what should a robot program do? What are the specifics of robot programming? Well, first of all, it needs to work together with a real-time operating system, because all our action, I mean, let's say 95% of the action should be online. You can do also offline programming, but this is a different story. For simulation purposes, you do a lot of offline programming, but all the execution is very important and the real-time constraints are very important, even because if you're doing sensor-based motion control, then you have to read sensor in real time and process this information in real time. We have seen the multiplicity of sensors that can be used for a robotic application, both proprioceptive and exteroceptive. So this should be something that is considered at the level of programming. And then motion control execution. So you command some motion, and we will see how to do this in particular at the kinematic level, but also at the dynamic level with torque commands. But this is a story that we will analyze in the second course of Robotics 2. But we should verify that these commands are executed. In parallel, the robot performs some task in its environment, so changes the status of the world. So if we want to model also what happens to the world, we have to keep track of changes due to the commands that we give to the robots, both in nominal cases and in case of perturbed situation, like a robot should pick up an object and bring it to a different place, but it loses on the way. It's a very unfortunate situation. But if I have sensor, I can discover this, so I should resume the situation, possibly go and pick up the object and then resume the original program. So this should be modeled in terms of status of the world and check of how the world evolves while the robot is doing their action. And this check is done with sensors, of course. Another very important aspect, which is more and more important, even in industry, I should say, is the interaction, both physical and cognitive, of a human with a robot. So they sharing the same workspace. They should coexist in the same environment without giving up safety, which is mandatory. So how this is integrated into a programming and a control architecture is also very important, as well as the fact that you should monitor your sensor or your actuator, and you should detect if there are faults, so that you can, especially in the presence of a human, this is a requisite for guaranteeing safety in all conditions. And then you should be able to recover from error if possible. For instance, you may have a robot with many joints and having a a failure of one actuator, so you can block that joint. Still you have some functionality left. If you have 8 degrees of freedom, one is gone, but with the 7 degrees of freedom, you may still do the task, provided that you reconfigure all your modules, algorithms, and so on. For instance, you have a Jacobian, which is no longer 6 by 8, but it's 6 by 7. But then you can do the same task, huh? So things like that. And then, of course, we're talking about programming, so there are languages. Huh? So what are the languages that characterize robotics? They are specific mainly in terms of data structure and of the set of instructions that are present. Otherwise, they are languages just like C++ or whatever language you're used to. Okay? There's a warning here, which will be clear later on, namely that the environment in which you program a robot depends also on the level in which you can interact with the various functionality of the robot itself. And when I talk about functional architecture, I mean what kind of task or device or robot level you want to enter and command. This will be clearer when in the second part, when we will talk about supervision architecture and how they can be decomposed in a modular way and how they should interact in a rather generic architecture. Okay, so let's talk about historically. There was a first generation of programming languages for robots, and this goes under the heading programming by teaching. What do I mean by that? Well, essentially, you could have a teach box, so a joystick or something similar to that, or a keyboard, and move in a manual way by pressing buttons or moving the joystick, the robot, to bring it into a specific configuration. Then you could learn this configuration, save this configuration, better said, and then move it to another configuration. So in fact, you're teaching the robot what to do by moving it in a very primitive way. And then once you have concluded this, you may insert this piece of elementary motion into a cycle, and then you can add to this cycle some option, do this until some switch turns on or turns off, and things like that. This was the first generation programming style, and those functionality are still there in more recent programs, languages. So it's something that you may use in some cases, but of course, it's not the only possibility. So, sorry, okay. So this was expressed in this way. So programming by directly executing the task, at least in some, let's say, clean situation, but maybe before the object were coming into the industrial process. So the operator guides manually or via a teach box the robot along some desired path or a sequence of nodes. When we are satisfied with the configuration that the robot has reached, we sample and store this configuration, and then may specify later how we would like to go from one configuration to the next one that we have taught to the robot. So this is a kind of a code skeleton expressed then in some instruction, and this instruction have some parameters, and you can modify the parameter of this program. So there were no really special need of programming, because the operator, which was not an engineer maybe, could do, according to his experience, the movement of the robot and save the execution in this way, and then later on one may decide if this cycle should be done at slow speed or a high speed or intermediate speed. There were also this option in a very generic way not putting numbers, but just putting percentages with respect to the maximum nominal speed of the robot, so that an operator should not really have very sophisticated programming skills. In this way, you could program various industrial tasks like spray painting or arc or spot welding, or even palletizing. You remember those tasks when we illustrated the various applications, especially in the industrial domain of robotics. These are historical, I would say, robot programming language, the T3 by Milacron or the Funky by IBM, who were built upon this skeleton. So they provide some data structure and instruction that accept this skeleton learned by teaching, and then could modify these elementary instructions. Second generation, this becomes more closer to what we are doing now. So this is a language, a structured language, so with option of flow of the program, typically interpreted, not compiled, and interactive in the sense that the user can modify it while the program is running, okay, eventually. There are the typical branching or while instruction. And if you buy a robot, all robot comes with their own programming language. And this is kind of disappointing, because if you had developed some program on a 6 degrees of freedom robot, you may think that if I change the Denavit-Artenberg parameter and I change the library of the kinematic function, I could repeat this exactly the same, which is not true because you have to change the coding. Although all these robot programs, one for each manufacturer, I would say, not one for each robot. So KUKA has its own language, Comau has its own language, Unimation used to have its own language when it was still alive, and so on. So if you don't change the brand, you can keep the same type of programming. So this was the most common situation. There was some effort many years ago, I should say, in order to try to find a standard for this. And the most advanced result that was found was not standardizing the language, but standardizing some modules which interface to the specific robot. So you can develop a program in your own language, and then you apply like a driver for a printer. The driver for the printer takes some generic instruction and specialize to the specific device. These things were done in the 90s in robotics. Well, the preferred way instead is to use any common language, Python, Java, C++, whatever, to develop libraries, possibly open source libraries, so that people can then combine, not do the effort of reprogramming everything from scratch, but combine things and then add their own specific needs and then convert the final result into, let's say, the specific commands of a robot, okay? Or even go without the programming language of the manufacturer, especially in research application. You can directly do your own programming up to the end. If you're using an industrial robot, you should always leave with some low-level instruction that are run in parallel to what you're asking to the robot, like checking that the motor are correctly operating, and in general, safety checking and coordination of reading and writing on input and output ports. So this is, let's say, the, I should say the low-level interface that you cannot get rid of. If you want to get rid of it, you should reproduce the same in your own code, which takes a lot of time. And you may not be qualified for using your software in some real application, just for research. So this is why when you're developing projects which have some or may have some industrial impact, you tend to develop your new results, your new algorithms, but then be able to interface with an existing controller with its own programming environment, because this is certified to work in practice. Okay, so there are a lot of critical aspects to be considered in this case. Otherwise, it's clear that using the most common languages would help. So here, the access here is at the action level. So with this type of programming, you really can drive the single motors, okay, of the robot. Moreover, remember that the robot is not a singleton in an application, especially in an industrial application. You have seen cells where multiple robots should cooperate and should exchange information through common buses. And so this type of programming languages for robots have also instruction and way to communicate with the external world, which includes other robots or other devices, machine tools, conveyor belts, and so on. And here there are a huge number of possibilities. Here I just mentioned a few. For instance, AML, when IBM was still producing robots, or VAL2, which was the latest version, including capability of handling vision or force sensor by Unimation, or PDL2 by Comau. This is the Italian leader in robots, or the KRL language by KUKA. And I put this in red because we have KUKAs downstairs, and I've used, just for illustration, the set of data structure and command of the KRL language. Okay, so how do you interface with KUKA? You will see this in the lab visit. This is the teach pendant. The teach pendant is kind of a notepad, so with a screen, a lot of buttons, a nice space mouse. So it's a mouse which has 6 degrees of freedom possibility, because this drives 6 joints. Okay, so if you move properly this space mouse, you can move, for instance, 1 joint at a time, or 1 coordinate at a time in the Cartesian space. Okay, so at this level, it's the teach pendant. So the user is teaching the robot what to do. And then you can switch in speed or move joint by joint incrementally by minimum increments by this type of buttons, okay, 6 and so on. Actually, this is a different story. When we received the 7 degrees of freedom lightweight robot by KUKA, which is still a research product, now has become an industrial product, they had the same interface. Although there were 7 joints, we have an interface with 6 pairs of buttons. So to access to one of these joints, we should alt switched or whatever to have this access. So not very friendly from this point of view. So this is the teach pendant. Then there is the programming through the KRL language, and the 2 things are integrated. So you can instruct some motion through the teach pendant by moving the robot, or write some code, or merge some skeleton code generated in this teaching mode with some other part which you programmed offline, and do things like that. The other things that is important is they have a robot sensor interface, RSI, XML, this is the coding which works in internet, and this is a way for interfacing the robot with external devices. So other robots or sensor, typically vision or force sensing or Kinect in different way. And there's another interface that KUKA developed, which is called FRI, Fast Research Interface, which is the same thing but applied only to the KUKA lightweight, and now also to the industrial version, which is called AIVA, as a robot assistant in industry. This fast research interface allows much better capabilities of entering into the low-level control layer of the robot. And it does at a much higher frequency. We will see that while there are cycles of, let's say, 12 milliseconds from one reading to the next one using the RSI interface, with the fast research interface, we can speed up to 1 millisecond. Okay, so 1 kilohertz, and which changed a lot of the story, what you can do in between, and how accurate you can be with your external codes and sensing. So this is the basic set of instruction. So if you start, I don't know if you can read it, but there are, of course, declaration of variable or some structure, and between the structure definition, you will have things like frames. Defining frames is basics for describing tasks. We have seen why, and also for describing some kinematics, which is coded inside the programming environment for this robot. But of course, you may wish to code some other task kinematics. For instance, you may be interested in some particular point in the chain, not just the end effector. So you may need to have access to the frame that describes the relative position of the link and stop at certain point, just like we have done with the chain of homogeneous transformation in the Dennevit-Artenberg convention. Okay. Well, this is very important. All programming languages for robot have some move instruction, because motion is principle of robotics. We have seen it's not just a computer, there is some motion in the real world. Here you see 6 types of motion commands. Each come with, this is described in a manual, reference manual. So they refer to some page of the manual. I've just taken out from there. So these are 3 absolute and 3 relative instructions. You see that circ or circ relative, lin or lin relative, and PTP or PTP relative. PTP stands for point to point, and it's a motion which is defined in the joint space. While lin and circ are motion which are defined in the Cartesian space, along a linear path or along a circular path. See, we can combine this and make much more sophisticated motion, or program ourselves some strange motion which is not a line and not a circle. But if we want to use their controller, our program should then decompose, no matter how complex is the path that we have defined, into this elementary path so that we can call their own laws. Okay, unless we define some low-level interface where we define directly the results of this planning at the joint level, and then the controller takes just new positions which are just sampled out of a very complex path. It's like solving inverse kinematics point after point. Okay, we will see how this can be done and what are the options when we will talk about trajectory planning in the Cartesian space or in the joint space. There we will see all option of, or a few options, the most important option for programming motion. Okay, and then here there are some instruction for controlling the execution of a problem, for continue, halt, if, then, loop, repeat until, cases, which goes like this. I forgot to say, this comes with some parameters. They are called with some parameters. Now, linear motion, it's a linear motion in the Cartesian space, of course, from one point to another point. So that has some argument when you call this instruction. Similarly, when you check and you switch your case, you may go and read some input ports or do something while writing on some output ports, so interfacing the robot with something outside. In fact, here you have input and outputs. You have typically analog input and analog output, or digital input, or the possibility of generated pulses or receiving pulses. For instance, pulses from encoders. Okay? And then you can break the system. This is an instruction which is set on the brakes, brakes on, brake off, or work under interrupt, so stopping some part of the program and executing something else until something happens, or trigger some of these instructions based on some information which is not specified in advance. For instance, trigger when distance is lower than, say, 2 centimeters, and this trigger is based on a sensor input, some sensor that provides the distance, and when this value goes below, then you switch to a different part of the program. Okay, so you see that with respect to standard programming language, there's nothing really new, except the fact that you are conditioned by events which are acquired from the real world through sensors. Okay, this is very important, even in this second generation. Okay, and then basic data set, as I said, there's a declaration there, but you have frame vectors, you have kind of mathematical library inside, so that you can do vector product, you can do inverse of matrices, at least of 4x4 matrices or whatever. Okay. So typical motion primitives. This is very important, so this is why I'm focusing here. So taking from the manual. So this is the point-to-point motion. Pay attention. It's represented in the Cartesian space. Because if I show you some joint motion, I can just show a plot of how the joint will vary, but you don't see exactly what happened. Now, you should see a movie or see the robot downstairs. But if I take a picture like that, so this point-to-point motion is a linear motion in the joint space. So if I want to represent this here, I would say, okay, I'm not doing it for that KUKA robot, but I'm doing for my good friend, the 2R. So I have some Q1 and Q2. And, okay, they should start from the same value. Okay. And then I'm saying that I want to go from this configuration, characterized by these 2 points, to another configuration, which is this one. So, and this at the same time. So this will go like this, and this will go like this. Okay? So this is a linear motion in the joint space, and this is programmed with the PTP instruction. Now, what happens to the end effector? When I'm moving linearly the joints, this does not mean, by no means, that the end effector moves along a linear path, just because there is all the trigonometry involved. So, and this is what you see here. So, point P1 is the direct kinematic mapping of the first configuration. Point P2 is the direct kinematic mapping of the second configuration. I'm moving linearly in the configuration space, but here is what the tool center point is doing, just representation, just to show that the two spaces are completely different. Okay? Indeed, it will start from P1 and go to P2, but there will be no linear motion in this case. To perform linear motion, you have to specify a Cartesian linear motion. Okay, so you specify for going from maybe the same point P1. Maybe this point P1 is a point where you brought the robot with the teach box. So he knows that, I mean, he's in P1, but he also stored the configuration. Okay? Now, when I store the configuration in Q1 and Q2, then it's very simple to command the linear path from Q1 to Q2, or from the initial to the final configuration. Here there's two joints, so there's some confusion. While it's very simple and visually very clear what I'm doing if I'm specifying a linear path, so with the linear motion in the Cartesian space. But remember, I cannot actuate directly the Cartesian motion because the actuators are in the joint space. So somehow I should convert this path, and we will see also the timing law that I use on this path, because I can move at constant speed or start with zero velocity, accelerate, then travel at some medium speed, and then decelerate and stop, and so on and so on. Now, all this motion should be converted into some commands at the joint level, because there is where the actuation takes place. This is why it's so important, direct and inverse kinematic, and differential and inverse differential kinematic at the velocity and acceleration level. Finally, if you give 3 points in the Cartesian space, and if these 3 points are not aligned, then you can define a unique circle going through the 3 points. So, since this is very common in the application, there's a special circular motion command, which is Cartesian, takes a start, an auxiliary point, and an end point, and generates a motion in the Cartesian space. Okay? What about the orientation of the end effector? Now, if I give you a path in a 3D space, this is a path of a point. It's not, nothing is said about the orientation. I could go linearly like this, going in a linear, or I can go linearly by changing my orientation. So something else should be specified in terms of orientation. And there are various options. The most common are keep the constant orientation. So you start with a given orientation, keep this orientation all the way through. Okay? Now, okay, let's comment the other option and then go back to this situation. Or you can use a set of angles to define the change of orientation. So you define a roll pitch yaw angle for the initial orientation, a roll pitch yaw angle for the final orientation, and then you interpolate, like here, in a linear fashion between the initial value and the final value of these angles. Okay? So you change orientation. It's not really evident what you're doing in between. In fact, we will see that for the orientation, there's a much better way of doing this by using the results of the axis angle representation. Okay? We will talk about that when programming. So this should be combined with this type of motion because we are working on the end effector level. When we are commanding motion in the joint space, we take for granted what happened in the Cartesian space. So we have no control, no special control on the path, nor on the orientation that the end effector is taking. But we are very fast because we are directly commanding motion in the joint space. We don't have to do this kinematic inversion, okay? Which is instead the case of when programming motion at the end effector level. Now, you can do whatever you wish with this programming. In particular, you can write a code. After you've brought the robot here in P1 and in P2, you can write a code that says go in linear along a linear Cartesian path from P1 to P2. But what if the robot, while moving, while executing this command, crosses a singularity? What happens then? Okay? So even if you can program this, you have always to check the actual result. This is why offline programming and simulation is very important, because you can discover some problem in advance. Otherwise, the robot will start executing the task and all of a sudden have increasing speeds at the joints until it saturates and some protection goes on and the robot stops. Okay, and this is something that you don't want to have when the robot is online executing some task. Okay, so remember that all the analysis is not thrown out of the window, even if we can program that way. In fact, the KUKA controller receiving such type of commands will do exactly what we learn in this room about inversion and inversion at the differential level, checking things and trying to stop in advance the motion or modify the motion so that the robot can go through singularity in a robust way. Okay? And we should know how this works, because if we want to do it for our robots, we have to reproduce this type of behavior. So this is why we learn all the mathematics that is behind. Otherwise, we would program and stop. As I said, data structure. Again. No? I don't know which is better. A bit better. As I said, there are frames. Frames are everywhere. And in the KRL language, they are preceded by a dollar. So this is the word frame, a base frame, a tool frame, a robot frame, which may coincide with frame 0 of the Denavit-Artenberg convention, and so on and so on. And then you can do computation. Once you have defined this frame, you can do computation which are either constant homogeneous transformation or homogeneous transformation that depend on some variable. For instance, the position of the tool with respect to the position of the base depends on the direct kinematics, like we have learned. Okay, so this is already embedded. And then, of course, you can move independently of how you define things in the Cartesian space and through frames. You can move independently each joint, and you should know what is the positive sense of rotation. And this is why you have pictures like that in all manuals of programming languages. So let's say a few more words about interfaces, because we want to do something that goes with this robot that goes beyond what the manufacturer also intended to do for industrial application. So this is why KUKA developed, actually developed this robot sensor interface, because in some industrial application, use of vision, use of force sensing is, may change radically performance or speed up cycle times. So this is why they provided to the generic user this sensor interface. And we use this channel to implement our codes and talk to the robot. Unfortunately, with a cycle of only 12 milliseconds, not faster than that. And so through this interface, you can acquire information from the system, for instance, position data of the joints from the encoders, or currents that circulate in the motors, and other signals like this, or send to the robot controller data, which are output commands coming from your own program, that commands, for instance, the joint velocity of the robot, or just sensor data, which are used within the programming language that we have seen before. So this second part, so not just the interface to sensors, is very relevant for us. Why? Because we are using sensor, but we interface sensor to our own, let's say, PC, do some elaboration, and then finally send commands of motion or reference position to the robot controller, to the embedded robot controller. So we are using mostly this interface for influencing the robot from one interpolation cycle to the next with our own code, which process external sensing. While KUKA itself intended this interface for directly interfacing sensor to their own programming code. Okay, so this is the main difference that we have here. So we can intervene to the path planning of the robot, so changing their own path planning. We can use the signals that we receive for doing some diagnosis. For instance, we have used this measurement of the current in the motor to discover if there is an extra collision with the environment or with some human. Okay, so this is something that we have added to it. And then there are more technical aspects so that we can use this protocol for communicating with other objects that are seen inside the programming environment as programming objects that exchange data in input and output. We won't go into the detail of this, so this is just for your reference if in the future you will happen to work directly on the KUKA KR5. And of course, there's a monitoring of timeout, because if you allow to enter some command data from your own program or to acquire some sensor information from your external sensor, then you have to set this limit of 12 milliseconds. If you take longer than that, some strange effect may happen, because the controller of the KUKA may read whatever it is on that port at that instant, and this may be a signal without any significance, or may be stuck waiting forever for this signal that is not coming. So the data exchange should be monitored, and there's an extra process doing this so that synchronization is kept, and you're not allowed to go beyond the 12 milliseconds, otherwise the robot goes into safety and stop itself. Okay, so if you're doing too much computation because you want to do many nice things with many sensors, and you do not respect this timing in real time, then the robot stops anyway. This is the monitoring of data exchange. So here I show you a couple of examples of use of this sensor interface. This is classical in a sense. So here you have a robot, you have the cabinet, you have some task where the end effector should enter in contact and apply some forces to this structure. Okay? So there's a tool and there's a force sensor. The force sensor may be an ATI device, so some external thing. It's not produced by KUKA. It's something that needs to be interfaced from the outside. It's not something that you can embed. So this is mounted on the wrist, at the wrist or close to the tool. And typically you may wish to have some motion in this direction V, which is activated only when you have reached some pressure in some direction. So only when the force X reaches some value. So how do you do this? You have to use the sensor interface to acquire force measurement from your force sensor, and we have seen that. The force sensor provides measurement in its own frame. Okay? So if you don't convert this externally, but just throw in this, the controller should know where the sensor is. In fact, there is some frame which moves together with the direct kinematics, then there may be some final offset added. So it converts this into its base coordinate, so into the x direction, reads then the force in the x direction, and if this is larger than some value, he knows that he's in contact and applies the right force, and then he could start moving. So in terms of commands, it may be some linear motion commanded in order that the system approaches, and then a command which is relative, so you provide linear motion along the direction of the velocity v, relative to the fact that the force sensing in the direction x is providing some input of, let's say, more than 10 Newton, okay? And then you start moving. So this is a classical way that you can do, and you render more autonomous your robot because you don't have to place things exactly in that way. There may be some uncertainty, and you compensate for the uncertainty by adding an external sensor. But then this external sensor needs to be read in real time and intervenes in the planning of motion, so in the programming aspect of the robots. Here, well, actually, here we have used without external sensing the robot. So some colleague of yours in a project of Robotics 2, they have commanded the robot's velocity by mimicking the presence of a virtual obstacle in the environment. So the robot is programmed to do a circular path in the Cartesian space, but then it hits this virtual surface and needs to modify its motion so that it doesn't penetrate this virtual surface until it is able to recover with the original motion. This is why they choose some cyclic path, circular or square path. Here they have a view in MATLAB. Here they have a view in WebBots. So there are programming environment where you can show also some graphical. Here a skinny version, here a more realistic version, and here is the actual motion of the robot as seen from a camera that overlooks things. So, see, without joint range limits or including virtual limits, this is, by the way, here we are commanding only a motion for the position of the end effector, so a three-dimensional task. We don't care about orientation. Since the robot has 6 joints, we will work here with a Jacobian, which is 3 by 6. So we are in a case, if we want to solve an inverse kinematic problem, we are exactly in a case where we cannot use, for instance, the Newton method as such. So inverting a non-square Jacobian, we should use the pseudo-inverse or the Jacobian transpose if we use the gradient method. So this is how it works. By the way, I think they built up things superposing the robot without the limits and then with the limits. So you see here on top, you will see 2 robots splitting. One is the robot without the virtual limits, so performing the full circle, and the other is the actual robot modifying its motion until, so from here you can understand that the circle was placed like this and it's cut on top for a while, okay? So just, I mean, what's the sense of this? Just to understand how to, was just starting, understanding how to let the robot sensor interface talk with a program developed in MATLAB or then converted in C++, whatever it was. Again, here you see the 2 robots differing. So, but I think that you get the point here to this interface. This is a maybe more interesting. This is a master thesis of Emanuele Magrini some years ago. Now he's doing the PhD with us, dealing with human-robot interaction and some additional stuff. So he was giving commands to both vocal commands and gesture commands to the robot. These were recognized by a Kinect, which was tracing his hands. And the vocabulary was very simple, like listen to me, so that the KUKA stops doing what they're doing and waits for some instruction. Or follow, or give me. Give me means come to the place where I put my right hand or left hand, or follow my right hand or left hand, or follow my closest end, my nearest end to you. So this may switch from one situation to the other and then stop the collaboration and whatever. So here again, we have a Kinect overlooking monitoring the environment, so recognizing the human, computing distances, and then moving the robot through the sensor interface. So every command, every 12 milliseconds. In this 12 milliseconds, the Kinect is processed and the commands are computed for the robot itself. So you maybe don't hear the voice, but you see here, KUKA, listen to me. You see the commands written to that. So give me, the end effector goes to the place where he recognized the, until he doesn't give a new command, the robot. So this is follow nearest hand. So it just first goes to the left hand. And you see now all joints moving, the 6th joint moving. You see also joint 4 rotating. This is interesting to see. Now he put the other hand, it becomes closer, and then the robot change situation. By the way, again, it's only position control for the end effector, so it has 3 degrees of redundancy. And this motion in the joint space is performed in such a way that this tool is always best visible from the Kinect. Okay, so we made this type of modification. This is very dangerous, by the way. This tool is very dangerous, but I mean, this is another story. Okay, and then the interaction ends. Okay. Now, what about the other interface, the fast research interface that now we are using more intensively? So this comes with the lightweight robot. The lightweight robot was bought in September 2012 with research found from the Safari project that we are coordinating. And this has a different way of working. So here, outside, you develop your custom code. And we developed codes for doing kinematic control, trajectory planning, resolution of redundancy, dynamic modeling, torque dynamic computation, physical human-robot interaction with contact with the human. A lot of things that we do for research. Okay, so we developed our program there. We have libraries. We have ROS nodes developed in that area. And it interfaces with their motion control kernel of the robot, so this part, at the rate which can go down to 1 millisecond, 2 milliseconds, 10 milliseconds, depends. I mean, this can be changed. Let's say that 2 milliseconds, so half a kilohertz, is very reliable. 1 millisecond, sometimes it goes some protection on. Okay. Of course, you can still use KRL commands there, or just go to the motion kernel and execute velocity command at the joint level, or torque command at the joint level. Torque commands are there if you have a dynamic model of the robot. We have done a dynamic identification of the model, all subject that will be dealt with in robotics too. Okay, So you see that, for instance, you have the way of acquiring current measurement or commands and receiving FRI commands from the outside. So this is the way in which they communicate. And this video, which is new, by the way, with respect to the previous, this is September 2014, just show, I mean, you don't care about what it does. Just illustrate the fact that we are able to command the lightweight robot, for instance, with velocity command at the joints. In particular, in this video, we were interested in generating commands at the velocity level, so Q dots, as if they were coming from an acceleration or a torque command, which is one differential level higher, and implementing this in discrete time, so that it reproduces exactly the same behavior of the second order control law, but it's much simpler to implement, provided that you do things properly, and still has the same accuracy. Okay? So this video shows a task. First, a task where we're commanding velocity. It should go through 4 points, so start from here, go here, and then stop here on top. And this is a velocity command. And you see that at some point the robot stops, because with this velocity command, some limit torque to the motor were exceeded. Okay? So we decided to do this scheme at the acceleration level, where commands are more smooth, and then we can compensate for this internal motion so that the whole task is executed. But the acceleration control law is very complex. So the idea behind this video is, let's have this discrete time implementation at the velocity level that reproduces the same behavior of the acceleration level command, okay, which is much simpler actually. Okay? And now at the end we compared the two, the execution. So now the orange robot becomes blue if we have the acceleration level control law, or green, you don't see there when you're doing things at the velocity level in this way. And you see here there are some differences which are very negligible. The two motions are exactly the same. So apart from what is this result, you may be interested or not, but this shows that you really have low-level access. You can command acceleration, you can command velocity, you can compare the things, and they are very reliable. Other uses of the FRI, well, these are taken from the literature. There are people that do coordination of dual arms, so they have one robot and another robot, either remotely or being the left and right arm of the same, mounted on the same torso of a humanoid-like manipulator. And the communication between the two controllers, these are two separate manipulators, are done through the fast research interface. And they both communicate to a unit that coordinates the motion. For instance, let one be the master and the other be the slave, or do simultaneous control so that they can apply forces to a common held object or things like that. Very similar here. This is very nice, I think. This is developed at the University of Siena. The fact that you can, instead of using, for instance, the space mouse of the teach box of the original KUKA controller, they use an haptic device, which is a structure, a very light structure, which acts like a joystick and has 6 degrees of freedom. You see, it's a parallel structure, if you can recognize. You put your fingers here on this side, and you can move these very light things in X, Y, Z direction, and then also change orientation. So you're moving with your hand like this, and you really feel what you're doing, and this becomes command for the end effector of the robot through the fast research interface. And if you had a force sensor mounted there, you can feel back some touch on your device. And if you don't have a sensor there, but you have a virtual reality environment that you set up, And when the robot in the virtual reality, the real robot is moving also in a virtual reality. In the virtual reality is hitting something, and you feel this on your command. So you have this haptic feedback. All realized, and for haptic feedback, every time you need for sensing, you should be very fast. While for controlling motion, you can also give up some speed in terms of communication. The information on force should be very fast, otherwise you go immediately unstable, which means that you try to, for instance, holding a force in contact, and the robot starts bouncing and vibrating in contact because of the delays in the communication. Okay, so it's very critical to have fast research, fast interface and command when you have contact and exchange of forces. Let me conclude with this. This is just a list of open source software that you may use, and you probably have already used some in other courses, that are relevant for robotics. And they are relevant both for real-time control, but also for simulation, for interfacing with robots, but also in general with other devices and sensors. Most of these are research-oriented. It's an open community, and typically this is an academic community, but the quality, I would say, that of this object is really excellent, and they are relatively easy to use. One project was the player stage, so this is a robot server for network robotics. It works under Linux or Mac OS system. And it can be interfaced to a large variety of hardware, and the stage version provides also a nice two-dimensional simulation environment. This has been expanded into a three-dimensional simulator, but this becomes then an independent project which goes under the name of Gazebo. And in Gazebo you can do really not only nice rendering, but also realistic physical simulation with an internal engine which is called ODE, which means ordinary differential equation, which means an integration of equation. So you define an object, you define the mass of this object and some inertial properties, and then the system automatically integrates the associated physical equation that describe the motion of this object when subject to forces and torques. Okay, so it's a very nice things. Or you can use VREP, as I said. VREP is not free in its full version. It's produced by Coppelia Robotics. I think it's a Swiss-based company. But there's an educational version that is free, and it's enough for our needs or your needs. And in this case, every body or object that you can define in CAD has embedded its own controller. So the description of how it behaves, how it moves. And the nice thing is that this is a user code that you can embed in any language, so in C++, in Java, or even in MATLAB, and so on. So this is very flexible, and the graphic is good enough. Then some of you may have used this in the courses with Professor Nardi. So there's OpenRDK. Did you encounter this already? OpenRDK? Okay, in any case, this is oriented for instance, in the RoboCup, we have a team headed by Professor Nardi and Professor Iocchi in our department. And there you have the single robot acting as agents, and they have to exchange and communicate in a highly dynamic environment because everything changes, including the opposite team. And so they use a kind of Blackboard type communication where each agent puts its own data and can read the data that other agents have put there with a kind of flexible and modular structure. The same thing happens with ROS. How many of you have used ROS or have heard about ROS? In which course? In robot programming. Again, same thing? Okay. So this again is what is called middleware. So this is an architecture where you can put elementary parts which are called nodes, so with a standard way of communicating with message passing. And again, they work, it's similar to this environment. In fact, I don't know if probably Nardi moved to ROS because now it's becoming the real standard, not only at the research level, but also some industrial users are starting using this. There's a wiki site where you can find whatever you need. And it's open source again, as all this list. Again, the Blackboard type is a mechanism of communication very similar with this publish and subscribe option. And ROS itself can generate you the structure of communication once you code the nodes in the proper way. So this is very, very... Of course, remember, it's a middleware because inside you have to put the meat. This is a way of organizing things. It's not the core. The core is inside the single nodes. So the real program, Python or C++ that you do, is inside one node or multiple nodes. ROS enables to let a larger architecture to work in a synchronized and coherent way. Well, this is another less information on that, just to have a list. So let me conclude today with this last slide, so ending the programming part. Of course, there is a third generation of languages. This is not real existing on the market, but it's much used in research. What is this? Well, it's from one side, if you compare with the development of conventional programming, from structured programming, you go to object-oriented. So there's a level of abstraction. It's called task-oriented because it's not really linked to a specific robot. It's more linked to the reasoning about how the world changes because of the action of the robot. Okay, so it's more, let's say, AI-oriented because you reason about things and you have to keep track of things. And the nice thing is that it's getting more and more cognitive. So it's reasoning not on a limited domain, but a domain which is open because it's dynamically changing and it's driven by the sensor information. Remember that the RoboCup, it's nice, it's fun to play, to program, to see it sometimes, but it's representative of a situation where things change in an unpredictable way, although within some rules. So it's very close to real life, independent of the fact that robots are playing soccer or whatever, okay? The scientific value of RoboCup is exactly the possibility or the need to develop things that understand and elaborate and are efficient in dynamically changing environment which are sensed by the robot. Okay, so this is important in general. So, and the access in this case, when we will, next topic will be the hierarchical organization of the supervision controller. And there we will have the robot level, the action level, and on top the task level, which is rather independent of the robot, I would say, because it's only related with what you should do and what are the actions that you should perform in order to reach some goal, independent of what robot you're using for doing this. Okay, so I think I'll stop here, and we will see on Monday. Have a nice weekend. So wait for my email with information on the new material.